Hello everyone. Welcome back to my course, Aerospace Engineering, Basics of Aerodynamics. In this video, we will talk about airfoil selection for aircraft performance. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Design requirements. When designing an airfoil, the shape of a wing or aerodynamic surface, engineers have to carefully consider a number of requirements to make sure it performs efficiently in flight. These design requirements can vary depending on the type of aircraft and its intended use, but there are several key goals that most airfoil designs aim to achieve. One of the most important objectives is to generate as much lift as possible before the airflow over the wing starts to separate, which can lead to stall. Think of lift as the upward force that keeps the aircraft in the air. The more lift you can safely produce, the better the aircraft can perform, especially during takeoff or tight maneuvers. At the same time, designers need to minimize drag, the resistance the air exerts on the wing, across a wide range of speeds and flight conditions. Reducing drag is like making the airplane slippery in the air, which improves efficiency and reduces fuel consumption. Another important consideration is controlling the pitching moment, which is the tendency of the nose of the aircraft to tilt up or down. A stable pitching moment is essential for smooth and predictable handling. Designers also focus on achieving a high lift-to-drag ratio, which essentially measures how efficiently the wing produces lift compared to the drag it generates. A higher lift-to-drag ratio means the aircraft can stay aloft longer with less energy, which is particularly important for long-distance flights. For high-speed aircraft, designers pay special attention to the critical Mach number, the speed at which portions of airflow over the wing first reach supersonic speeds. Beyond this point, shock waves and other high-speed effects can increase drag and affect stability, so careful shaping of the airfoil is needed to maintain efficiency and control at these speeds. Recently, there has been a lot of interest in designing airfoils for drones and other small unmanned aerial vehicles that operate at very low speeds. These aircraft encounter low Reynolds numbers, a measure of the ratio of inertial forces to viscous forces in the airflow, which dramatically affects how air moves over the wing. At low Reynolds numbers, the airflow behaves differently than at higher speeds, often causing lower aerodynamic efficiency. Understanding how the boundary layer, the thin layer of air close to the wing, transitions from smooth, laminar to turbulent flow is critical for designing airfoils that perform well in these conditions. Even small design tweaks can make a big difference in lift, drag, and overall efficiency for low-speed UAVs. In short, designing an airfoil is a careful balancing act. Engineers must optimize lift, minimize drag, control stability, and adapt the design for the specific flight conditions, whether that's supersonic speeds for fighter jets or low-speed efficiency for drones. By understanding these principles, designers can create wings that perform effectively in a wide variety of situations. Airfoil geometry. The geometry of an airfoil, the shape of a wing or aerodynamic surface, is fundamental to understanding how it generates lift and interacts with airflow. At its most basic level, an airfoil is described by its profile shape or envelope, which defines the curvature of its upper and lower surfaces. Airfoils can be symmetric, meaning the upper and lower surfaces are mirror images of each other, or they can be cambered, where the upper and lower surfaces have different curvatures. Cambered airfoils are designed to generate more lift at lower angles of attack. Some specialized airfoils feature what is called reflex camber, where the trailing edge curves upwards slightly. Reflex camber is commonly used in designs such as flying wings, helicopters, and autogyros to improve stability and control. We learned about wings' geometric measurements on our previous lessons. Let's dive deeper and learn more about them. A key geometric measurement for any airfoil is the chord, which is the straight line distance from the leading edge at the front of the airfoil to the trailing edge at the back. While the chord gives a basic sense of the airfoil's size, more precise geometric definitions are necessary when designing or analyzing airfoils. Important parameters include the maximum thickness and its position along the chord, the maximum camber and its location, and the shape of the leading edge, often defined by its radius of curvature. These details all influence the aerodynamic behavior of the airfoil, including lift, drag, and stability. In most airfoil designs, the thickness is applied perpendicular to a mean camber line. The mean camber line represents the average curvature of the airfoil and plays a critical role in shaping both the upper and lower surfaces. The amount and shape of this camberline determine how the airfoil interacts with the flow, and it affects key aerodynamic characteristics such as lift, drag, and pitching moment. The envelope of the airfoil, the exact coordinates of the upper and lower surfaces, can be formally defined and tabulated for a variety of purposes, including plotting, creating computational fluid dynamics grids, or generating designs in computer-aided design and manufacturing systems. The leading edge shape, often described by the nose radius, is particularly important because it strongly affects how the airflow attaches to the airfoil, influencing lift generation and stall behavior. Other key geometric parameters are expressed as ratios relative to the chord, such as the maximum thickness to chord ratio and the maximum camber ratio. The positions of these maximum values along the chord are equally important, as they can significantly influence aerodynamic performance. For example, increasing the camber near the leading edge can raise the maximum lift coefficient, which is beneficial for lift generation, but it also increases the pitching moment, affecting the stability and control of the aircraft. In short, every detail of an airfoil's geometry, from the curvature of the surfaces to the position of maximum thickness and camber, has a direct impact on its aerodynamic behavior. Understanding these geometric parameters allows designers to fine-tune airfoils for specific performance goals, whether for high lift, low drag, or stable flight characteristics. NACA method of drawing airfoil shapes. The systematic study of airfoil shapes and their aerodynamic characteristics began in the early 1920s in both Europe and the United States. Researchers at that time were interested in measuring how different airfoil profiles behaved in airflow, and they organized their findings into families of airfoils that produced predictable aerodynamic characteristics. With these catalogs of measured data, aircraft designers could efficiently choose an airfoil that best suited their specific application, whether it was for maximizing lift, reducing drag, or achieving stable flight. In the United States, the National Advisory Committee for Aeronautics, or NACA, carried out the most thorough and systematic studies of how airfoil shape affects aerodynamic performance. By analyzing existing cambered airfoils, such as the Clark Y and Göttingen sections, NACA researchers identified shapes that were already known from early wind tunnel experiments to have excellent aerodynamic characteristics. These airfoils served as a foundation for NACA's work. The researchers observed that if the camber was removed, these airfoils shared a geometrically similar shape. By standardizing the thickness-to-chord ratio and applying a polynomial curve fit, they were able to define the airfoil thickness in a precise, repeatable manner. This process resulted in the development of the classic NACA U0 series symmetric airfoils, which became the basis for many subsequent NACA airfoil families. These 00 series airfoils were symmetric, meaning their upper and lower surfaces were mirror images, and their geometry could be described mathematically, making them ideal for systematic analysis and design. By establishing a method to generate airfoil shapes mathematically, NACA not only made it easier for engineers to select airfoils for specific aerodynamic requirements, but also provided a foundation for further innovation in airfoil design that continues to influence aircraft and UAV development today. Geometric construction. In the NACA method for defining airfoil shapes, a coordinate system is established with its origin at the leading edge or nose of the airfoil. The airfoil's geometry is then described in terms of the horizontal x distance along the chord and the vertical y distance from the chord line. This provides a clear mathematical way to locate any point on the airfoil surface. The airfoil profile is constructed by combining two key components, the thickness distribution and the camber line. The thickness, denoted as YTX, defines how fat or thin the airfoil is at each point along the chord, while the camber line, YCX, defines the curvature of the airfoil. To create the final shape, the thickness is plotted perpendicular to the slope of the camber line at each point. This ensures that the upper and lower surfaces of the airfoil correctly follow the intended thickness while maintaining the desired camber. By following this systematic geometric construction, engineers can precisely define any NACA airfoil shape mathematically. This method allows for accurate plotting of the airfoil coordinates, which is essential for both aerodynamic analysis and for practical applications like computer-aided design, computational fluid dynamics, and manufacturing. It's a structured approach that transforms what might seem like a complex curved surface into a series of calculated points, making airfoil design both repeatable and precise. Nose radius. The curvature of the airfoil's nose, or leading edge radius, denoted as RT, must be precisely defined when constructing the profile. This is typically done using an inscribed circle. To locate the center of this circle, a straight line is drawn from the origin of the coordinate system at the leading edge, with a slope equal to the slope of the camber line at a small distance along the chord, typically around x equals 0.005. The center of the circle is then positioned by moving along this line a distance equal to the desired leading edge radius. This point becomes the center of the nose circle, which defines the curvature of the leading edge. It's important to note that the center of the nose circle does not lie directly on the mean camber line, but slightly above it, reflecting the natural curvature of the airfoil's nose. One consequence of this construction method is that the leading edge of the airfoil may extend slightly beyond the y-axis. In practice, this small protrusion has negligible effect on aerodynamic performance and can generally be ignored. For symmetric airfoils, however, the center of the nose circle lies directly on the x-axis. Once the circle is defined, it is carefully blended into the upper and lower surfaces of the airfoil profile. Special attention must be given to this blending step when implementing the geometry numerically, as accurate integration of the nose shape is important for ensuring realistic aerodynamic behavior in analysis or simulation. trailing edge shapes. Airfoil sections can have different shapes at the trailing edge, which is the rear end of the airfoil where the upper and lower surfaces meet. In practice, there are three general types of trailing edge shapes: convex, finite angle, and cusped. It is important to note that in real airfoils, the trailing edge always has a finite thickness. It is never infinitely thin, so each shape represents a slightly different way the airfoil tapers at the rear. The convex trailing edge curves outward away from the airfoil surface, forming a smooth, rounded end. This shape creates a sharp edge that terminates at a finite angle relative to the airfoil surface. Finite angle trailing edges are designed to end at a clear angle and are commonly used in many standard airfoil designs to achieve balanced aerodynamic characteristics, such as lift and drag performance. A cusped trailing edge, on the other hand, comes to a sharp, pointed tip. This type is less commonly used and is typically reserved for specialized airfoils where precise control of airflow and delayed flow separation are critical. The choice of trailing edge shape depends on the specific aerodynamic goals of the design. For example, designers may select a particular trailing edge shape to maximize lift, reduce drag, or control the stall characteristics of the airfoil. By understanding these differences, engineers can tailor airfoil performance to meet the exact requirements of the aircraft or application. Circle method of airfoil construction. The circle method of airfoil construction is a geometric technique used to define the shape of an airfoil, particularly the leading edge and the upper and lower surfaces. In this method, a circle serves as a reference to generate the curvature of the airfoil's nose and to establish points along the surface. The center of the circle is carefully positioned based on the desired leading edge radius, and the circle is then blended smoothly into the upper and lower surfaces of the airfoil. By plotting points along the circumference of the circle and connecting them with the rest of the airfoil profile, the designer creates a continuous, aerodynamic shape that satisfies both geometric and aerodynamic requirements. This method is especially valuable because it provides precise control of the airfoil's leading edge curvature, which strongly influences airflow attachment, lift generation, and stall behavior. Once the nose is defined, additional points are plotted along the upper and lower surfaces to match the intended thickness distribution and camber line. The result is a smooth, well-defined airfoil that integrates all critical geometric features. While primarily a geometric approach, the circle method offers a practical and visual way to construct airfoil shapes before using more advanced tools such as computational fluid dynamics or computer-aided design. It ensures consistent surface curvature, accurate integration with the camber line, and reliable preliminary airfoil design. Another closely related graphical approach involves drawing the airfoil as a series of circles. In this method, each circle has a radius equal to the thickness distribution, denoted as yt, or in a non-dimensional form as yt equals yt divided by c, where c is the chord length. The centers of these circles are placed along the camber line, using it as a backbone for the airfoil. The upper and lower surfaces are then formed by drawing smooth curves that are tangential to all of the circles. This graphical technique provides a simple and intuitive way to visualize how an airfoil shape is generated, showing how thickness and camber combine to form the complete profile. It is particularly useful for teaching purposes or for gaining an intuitive understanding of airfoil geometry. However, while the method is excellent for visualization, It is generally preferable to construct the airfoil surfaces numerically, calculate precise coordinates, and tabulate the data points as described earlier. This ensures greater accuracy and allows the airfoil to be used directly in CFD simulations, CAD models, and manufacturing processes. Symmetrical NACA airfoils. Symmetrical airfoil sections are often chosen for the horizontal and vertical tail surfaces of airplanes and other aircraft because they provide balanced aerodynamic characteristics and predictable behavior. A well-known family of these airfoils is the NACA 00 series, sometimes written as 00XX, which refers to 4-digit symmetrical sections. The shape of the airfoil is defined in terms of its upper and lower surfaces, which mirror each other along the chord. The thickness of the airfoil at any point along the chord determines how fat or slim the profile is, and the thickness to chord ratio indicates the overall size of the airfoil relative to its chord length. For example, a NACA 0015 airfoil has a thickness equal to 15% of the chord. To accurately define the shape, designers plot the coordinates of the upper and lower surfaces at many points along the chord, typically 50 to 100 points, to ensure a smooth and precise profile. An important feature of symmetrical airfoils is the leading edge nose radius. This rounded nose is blended into the upper and lower surfaces to create a smooth circular shape. Including the nose radius is critical because it prevents the leading edge from being pointed, which would negatively affect the airflow and overall aerodynamic performance. By following these design principles, the NACA 00 series airfoils provide a reliable, symmetrical shape suitable for tail surfaces and other applications where a camber-free profile is desired. These airfoils are widely used because they combine simplicity, aerodynamic efficiency, and ease of construction. Cambered NACA airfoils. Cambered airfoils are created by distributing the airfoil's thickness around a mean camber line, which defines the curvature of the airfoil from the leading edge to the trailing edge. The camber line determines how much the airfoil curves and where this curvature reaches its maximum along the chord. To construct the airfoil, the thickness is plotted perpendicular to the camber line, producing the shapes of the upper and lower surfaces. NACA offers a variety of camber line profiles, including the 2-digit and 3-digit series. In these designations, the first 1 or 2 digits indicate the amount of camber, while the next digit specifies the location of the maximum camber along the chord. For example, a NACA 2408 airfoil has a camber of 2%, with the maximum camber located at 40% of the chord length and a thickness of 8% of the chord. By adjusting these parameters, designers can tailor the aerodynamic characteristics of the airfoil, such as lift, pitching moment, and stall behavior, to suit specific performance requirements. Supersonic airfoils. While well-rounded, cambered airfoils are ideal for subsonic flight because they generate good lift and have favorable aerodynamic characteristics. They are generally unsuitable for high-speed and supersonic flight. At supersonic speeds, air behaves differently, and the shape of the airfoil must be adapted to reduce drag and maintain stability. Supersonic airfoils are therefore designed to be very thin, with a low thickness to chord ratio, and to have sharp leading edges. The geometric shapes of supersonic airfoils typically fall into two categories. One type, called a double wedge airfoil, is formed from angled planes that create a thin, pointed profile. The other type, known as a biconvex airfoil, consists of two opposing circular arcs that produce a similarly thin section. The sharp leading edges of these designs are crucial because they prevent the formation of a detached bow shock in front of the airfoil, which is a major source of drag known as wave drag. By keeping the airfoil thin and sharply pointed, supersonic designs minimize wave drag and perform efficiently at high speeds. Supercritical airfoils. As commercial airliners have been designed to cruise at ever higher speeds, approaching the speed of sound, particularly at transonic Mach numbers above 0.8. A new type of wing shape was developed to address the unique aerodynamic challenges in this regime, the supercritical wing. A supercritical wing incorporates a specially designed supercritical airfoil, which reduces the strength of shock waves and, as a result, decreases wave drag. The principle behind this design is to carefully control the airflow so that it transitions to supersonic speed over the upper surface of the airfoil in a controlled manner and then recompresses smoothly. This delays the onset of supercritical flow, reducing drag at a given free stream Mach number or allowing the aircraft to fly faster before a sudden rise in drag occurs. The classic supercritical airfoil has a distinctive shape. It features the point of maximum thickness farther back along the chord than conventional airfoils, a relatively flat upper surface with only slight camber and often significant camber near the trailing edge. This aft camber compensates for the reduction in lift from the forward part of the airfoil. Supercritical airfoils were extensively studied and refined during the 1960s by Richard Whitcomb and NACA, leading to designs that could maintain efficiency at high subsonic and transonic speeds. Today, virtually all commercial jet airliners use some form of supercritical airfoil, allowing them to cruise efficiently at Mach numbers above 0.8 while minimizing wave drag. Laminar flow airfoils. Sailplanes and certain specialized aircraft often use laminar flow airfoils, which are designed to maximize the region of laminar flow over the airfoil's leading edge. By maintaining laminar flow over a large portion of the surface, these airfoils significantly reduce skin friction drag, improving overall aerodynamic efficiency. A well-known series of these airfoils was developed by Franz Xavier FX Wortmann specifically for sailplanes, commonly referred to as FX airfoils. The geometric shape of laminar flow airfoils is different from conventional airfoils used on most airplanes. One key feature is that the point of maximum thickness is located closer to the midchord rather than toward the front of the airfoil. This configuration creates a favorable pressure gradient over the leading edge, which helps the boundary layer stay smooth and laminar farther downstream. The benefit of this design is a notable reduction in skin friction drag, which is critical for high-performance gliders and low-power aircraft. However, there are trade-offs. Laminar flow airfoils generally produce lower maximum lift coefficients, meaning they tend to stall at lower angles of attack compared to conventional airfoils. They are also extremely sensitive to surface conditions. The airfoil must be glassy smooth and free of imperfections such as dirt, bugs, or fingerprints in order to achieve the intended low drag performance. Despite these challenges, laminar flow airfoils remain an important design choice for sailplanes and other aircraft where minimizing drag is essential. Propeller airfoils. Propeller airfoils refer to the cross-sectional shapes of propeller blades, and they play a critical role in how effectively a propeller converts rotational motion into useful thrust. As a propeller rotates, each blade section behaves much like a small wing, producing lift in a direction that contributes to forward thrust. The aerodynamic characteristics of these airfoil sections therefore directly influence the overall efficiency, thrust capability, and operating limits of the propeller. Historically, propeller airfoils were strongly influenced by manufacturing constraints, particularly for metal propellers. One of the most widely used airfoils was the flat-bottom Clark Y series, which features a nearly flat lower surface. This geometry simplified manufacturing while still providing acceptable aerodynamic performance. Another airfoil that saw use in propeller design was the RAF-6 airfoil, often with a gradual reduction in thickness toward the blade tip. At the outer portions of many traditional propeller blades, designers commonly selected the NACA 16 series, which was developed for transonic applications. This airfoil family is characterized by its maximum thickness located near the midchord, around 50% of the chord length, and a relatively sharp leading edge with a small leading edge radius. These features help the airfoil perform better as local flow speeds approach the speed of sound. In many modern propeller designs, a combination of airfoil sections is used along the blade span to match the varying aerodynamic and structural requirements. The Clark Y airfoil is often retained over the inner half of the blade, where structural thickness is important and Mach numbers are relatively low. Moving outward along the blade, designers gradually transition to airfoils from the NACA 16 series, sometimes adding camber to improve performance. This transition allows the outer blade sections to benefit from the higher drag divergence Mach number of the NACA 16 airfoil, which delays the onset of rapid drag increase associated with compressibility effects. At the extreme blade tips, the airfoils are made as thin as structural considerations allow. The underlying aerodynamic objective is to delay the formation of supersonic flow regions when the propeller operates at high airspeeds and high helical Mach numbers, thereby reducing losses in thrust and efficiency that would otherwise occur. Advances in aerodynamic understanding and manufacturing techniques have enabled the development of more sophisticated propeller blade shapes. Modern designs carefully tailor the local blade section angle of attack so that each portion of the blade produces near optimal lift with minimal drag. During the 1970s, a significant step forward occurred with the development of the ARA-D series of propeller airfoil sections by the Aircraft Research Association. These airfoils were specifically created to overcome earlier manufacturing limitations, particularly in anticipation of composite propeller blade construction. Compared to older airfoils, the ARA-D series featured increased camber on the lower surface, which enhances lift, along with a drooped leading edge that helps prevent stall at high angles of attack. The leading edge radius was also made more rounded to improve aerodynamic behavior under demanding operating conditions. Structural requirements remain an important factor in propeller airfoil design, especially near the blade root. Thicker airfoil sections are necessary in this region to withstand bending loads, torsional stresses, and centrifugal forces generated by rotation. In the ARA-D series, the position of maximum camber varies depending on the local Mach number. For low sectional Mach numbers, the maximum camber is placed far forward, at around 10% of the chord, which improves lift characteristics. As Mach number increases, the camber location moves aft to approximately 30% of the chord, a change that helps delay shockwave formation and the associated rise in drag. At very high Mach numbers, such as a local Mach number of 1.0, the ARA-D airfoil becomes extremely thin, with a thickness to chord ratio of only 3%, while still maintaining a modest camber of about 5%. In all cases, the trailing edge of the airfoil is intentionally made blunt to accommodate manufacturing constraints. The overall purpose of these advanced airfoil designs is to improve aerodynamic performance across the entire blade span, particularly in high-speed applications where helical Mach numbers are large. By delaying shock formation and reducing drag rise near the blade tips, these airfoils allow the propeller to maintain higher thrust and efficiency over a wider operating range. The ARAD series and similar modern airfoils significantly outperform older designs by carefully optimizing camber and thickness distributions, improving the lift-to-drag ratio of each blade section, and reducing the likelihood of stall at high thrust settings. As a result, modern propellers achieve higher propulsive efficiency, which is essential for high-speed propeller-driven aircraft, while also benefiting from reduced noise due to weaker shock waves and improved fuel efficiency. Summary and closure. Selecting the most appropriate airfoil section is a critical factor in the success of wing design, whether for subsonic, transonic, or supersonic flight, as well as for specialized concepts such as rotary wing aircraft and unmanned aerial vehicles. Different airfoil shapes are geometrically tailored to achieve the best aerodynamic performance under specific flight conditions, optimizing parameters such as lift, drag, and overall efficiency. For example, thicker, more cambered airfoils with rounded noses are better suited to slower flight speeds and low Mach numbers. These airfoils generate higher lift at lower speeds, making them ideal for aircraft that operate predominantly in the subsonic regime. On the other hand, thin airfoils with sharp leading edges are preferred for high-speed and supersonic flight because they minimize drag and prevent the formation of strong shock waves. Special airfoil designs, such as supercritical airfoils, have been developed for transonic flight where many commercial airliners operate. Supercritical sections reduce wave drag and help prevent boundary layer separation behind shock waves, allowing aircraft to cruise efficiently at speeds approaching the speed of sound. By carefully choosing the airfoil shape for the intended flight regime, engineers can ensure optimal aerodynamic performance, fuel efficiency, and overall effectiveness of the wing or aircraft design. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following is a primary objective when designing an airfoil? The correct answer is to generate maximum lift before airflow separation. Question 2. What distinguishes a cambered airfoil from a symmetrical airfoil? The correct answer is it generates more lift at lower angles of attack. Question 3. Why are supersonic airfoils designed to be thin with sharp leading edges? The correct answer is to prevent the formation of a detached bow shock and reduce wave drag. Question 4. Which feature of a supercritical airfoil helps reduce wave drag in transonic flight? The correct answer is maximum thickness positioned aft and a relatively flat upper surface. Question 5. What is a key limitation of laminar flow airfoils such as FX airfoils used on sailplanes? The correct answer is they produce excessive drag at low speeds. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about aerodynamics of aircraft fuselage and jet engines. See you in the next video. Bye.